Hello, this video is about the beauty of Galois extensions. Our proper name is trace, norm, and then computing inverses in Galois extensions. Just to informally recall what is Galois, it's an extension of fields which is as symmetric as possible. Namely, the size of the symmetry group of the automorphism group of this larger field over the smaller is equal to the maximal possible value, the degree of the extension. So we will use this condition, this amount of symmetries, to construct certain quantities called trace and norm, and to use one of them to effectively invert any number. That's the plan. The first statement, the first construction is about the subfield of invariance. Let me say what it is. Here's a notation. I'm looking at invariance in my larger field in the extension. I'm looking at elements which are invariant under all symmetries. So mathematically there will be elements in the field stable under all automorphisms. You could check, it follows just from the homomorphism properties of these, that this is closed under all arithmetic operations, so hence it's a subfield in F. You could also check by the very definition of that subfield that elements of K, which are to be fixed by automorphisms, that's the notation here, will be among elements of this subfield. So we'll have this intermediate subfield situation. So this field, let's call it L, sits in between the base K and the extension L. So this is called the subfield of invariance with respect to the, in this case, the full symmetry group. So let's look at what we have. Well, we have L, this subfield of our interest, sitting inside F. So we can compute the index. And the index of L in F will be definitely not smaller than the index of K in F. Because K definitely is inside L. And there was a result which we checked quickly before, that the index is always the upper bound for the symmetry group. So we can write the below bound for this index by the size of the symmetry group of this extension F over L. But let's look at what the symmetry group definitely contains. So any symmetry which fixes L, by the definition, it also fixes K, so the other way around, sorry. Any symmetry which is from this group will be acting on the F and will be fixing the subfield L. So let me write what I just say, that the group of symmetries of the initial extension will be definitely inside the group of symmetries of the extension reconstructed by changing K to L. Again, any symmetry in here, any phi, will be an automorphism of F, and elements of L by the definition will be fixed by that phi. So we have this inclusion, and hence we have the bound, the inequality between the orders of these groups. So now let's look what we have. We have this bounding from below this and so on up to here. But our original condition was that this extension is Galois, so these extreme numbers are the same, and so all the numbers in between are the same. So these numbers are the same and these numbers are the same. And if these numbers are the same, it would be just saying that the dimension of L is the same as dimension of K, over K is 1. So L is, as a vector space over K is of the same dimension, it must be K, because K sits inside. So we proved from the Galois that since these are equal, K is equal to L, and that is equal to this subfield of invariance, right? L is just a name for it. So we proved that the subfield of invariance is nothing but the scalars, nothing else is fixed. If you think about it, it's kind of an expected result, but we have this argument which works in the condition that the extension is Galois, so this condition is important. Let's now put this fact into use. Let's look at some applications. So applications will be two constructions, two functions on the larger field F, which will have values in the base K. The first construction is additive. The meaning of both construction is that we will just take any element in our extension F and we will do something with it, and we will get an element which is manifestly invariant under all symmetries. And as such, it must be an element of K. So the first additive construction is just the averaging. We take all automorphisms applied to our chosen X, so all automorphisms, and take the sum. This clearly is invariant, because if we apply any more automorphisms to it, it will be just reshuffling summands and not changing the sum. So the sum is an element of K, and it is called a trace of X. So the trace over K of F element X. And that trace function is the function from F to K, and it is additive. Meaning that the trace on the sum is equal to the sum of traces. And moreover, if we take an element of K, it will be fixed by all this, and it means that it will be just replicated as many times as the degree or as the automorphism group order. So that is the first application, the first construction. That is a trace. Let's look at another arithmetic construction we could do with all the symmetries applied to a fixed element X. Instead of summing them up, we can take the product. So this time the construction is multiplicative. It is called the norm. It is also an element in K, because the result is manifestly invariant under all automorphism from our symmetry group. So this is also an element in K. We have a function, this norm function from F to K. Now it is multiplicative, because we define it by just the product. So this is called the norm. And more precisely, this multiplicativity gives a homomorphism from the multiplicative group of F to the multiplicative group of K. So it is clear that if we start with something non-zero, then the result must be non-zero, because we have just the product of things which are non-zero. So that is the key to writing down a compact recipe formula for finding inverses. Inverse to an element in our larger field F. So what we can do, we can just take this product. So one of those factors is X itself, and the rest of those factors is effectively the inverse. Well, it's not exactly that X times the rest. Let me just write the rest here. It will be all the symmetries but the one which gives us x, which is the identity applied to x and then taken the product of those. So that is multiplied with x will give us the norm, which is not quite 1, but next best thing. We can divide by it because now we know that this is non-zero, and that is an element in the base, a scalar, which can be divided by easily. So the denominator here is just the norm of x. And that is, I consider as an achievement. So let me illustrate it in the simplest possible example first. Let me take, say, as f the Gaussian rationals. So I'm looking at this extension. I'm interested in finding inverses to elements. What are elements? Well, of course, they are just pairs of rational numbers. So finding the inverse is supposed to give us an expression like that. So let's just write well-known formula for inverting following this procedure. The group of symmetries, the group of automorphism group of this extension is of course cyclic group, and is generated by complex conjugation by the automorphism which changes I into minus I. So that is just, I'll just call it phi negative 1 because it will be taking the inverse of I. So that is the only non-trivial, that is as a group isomorphic to a cyclic group of order 2, that is the only non-trivial symmetry, so that is the only factor upstairs. And downstairs I have to compute the norm. So what is the norm? Is the product of the norm is the product of the number and its Galois conjugate, which changes I into minus I, so that is nothing but the sum of squares, of course. And that is our denominator here. And we could divide it into the two coefficients and have our familiar formula for inverting a Gaussian or any complex number. That is it. See you later.